During the summer, Mountain Rescue Team A receives calls for help randomly with a rate of 0.4 per day. Find the probability that during the summer, Mountain Rescue Team A receives at least 19 calls for help in 28 randomly selected days. So if we say X is the Poisson distribution for one day, so it will be a Poisson 0.4, then we can say that Y is the Poisson for 28 days, and we calculate that just by doing 28 times 0.4 in here, and therefore the mean number of calls is 11.2. We're then after the probability that Y is greater than or equal to 19. Now, some calculators have the facility to do that. If yours doesn't, then you'll probably have to do 1 take away the probability that Y is less than or equal to 18. There are no tables for this particular Poisson, so you're going to have to use your calculator. And when you do that, you'll find that it is 0.0208 to 4 decimal places. The leader of Mountain Rescue Team A randomly selects 250 summer days from the last few years. She records the number of calls for help received on each of these days. Using a Poisson approximation, estimate the probability of the leader finding at least 20 of these days when more than one call for help was received by Mountain Rescue Team A. So, this was part A. Let's look at part B here. So we know that for one day, it is a Poisson 0.4. We're looking at more than one call for help. So we're looking at X is greater than or equal to 2. And the probability of that is 0.06155. Again, if your calculator won't do it that way around, you're going to need to do 1 take away the probability that X is less than or equal to 1. And so we can form a new distribution, which I'll call A, because they're insistent that we use different letters for every different distribution. And so that is going to be a binomial with 250 trials. That's the 250 days that she selected. And the probability of success being 0.06155. So now what I'm going to have, probably B is not the best letter to use, is C, which is the approximation. And that's going to be a Poisson using the mean for this binomial, which we get as 250 times 0.06155. And if we do that, that ends up being a Poisson 15.39. And then what we're after it being greater than or equal to 20. So we're after the probability that C is greater than or equal to 20. So that's the at least 20 part here. And again, on your calculator, if it won't do greater than or equal to 20, just do 1 take away the probability that C is less than or equal to 19. And if you do that, you'll get 0.1475, correct to 4 decimal places. Mountain Rescue Team A believes that the number of calls for help per day is lower in the winter than in the summer. The number of calls for help received in 42 randomly selected winter days is 8. We want to use a suitable test at the 5% level of significance to assess whether or not there is evidence that the number of calls for help per day is lower in the winter than in the summer. We want to state our hypotheses clearly. So that's the first thing we should do. Always get your hypotheses done first. So h naught, our lambda, is going to be 42 times 0.4, which is 16.8. Remember, it's 0.4 per day for the summer. The alternative is going to be that it is lower in the winter. So our original assumption, the null hypothesis, is that there is no deviation from the summer, and then our alternative is what they suspect, that it might be lower. So let's have a distribution D, which is a Poisson 16.8. So assuming the model is correct. Now remember, 42 random days gave us 8. So we're after the probability that D is less than or equal to 8. And the calculator should work for this time. And that would give us 0.0141. And that is less than 0.05, which is the 5%. That is therefore in the critical region. So reject h naught. There is now evidence of fewer calls per day in winter. During the summer, Mountain Rescue Team B receives calls for help randomly with a rate of 0.2 per day, independently of calls to Mountain Rescue Team A. So it's 0.2 per day, and independently is important here. That means that if we say E is the daily rate for the two teams, that is going to be a Poisson 0.4 plus 0.2, where 0.4 was the rate for A and 0.2 the rate for B. So that's a Poisson 0.6. The random variable C, I've already used C once, but I don't think it will matter here, is the total number of calls for help received by mountain rescue teams A and B during a period of N days in the summer. On a Monday in the summer, mountain rescue teams A and B each receives a call for help. Given that over the next N days, the probability C equals 0 is less than 0.001, calculate the minimum value of N. Well, it's N days, so our Poisson is just going to be 0.6 N. And we're after the probability of C being 0 being less than 0.001. Now, the only way really of doing this is to use this. But it's not too bad when we're looking at the situation of 0, because that just becomes e to the negative lambda, lambda to the 0 over 0 factorial. And lambda to the 0 and 0 factorial are both 1. So it just becomes e to the negative lambda. And our lambda here is 0.6 n. So what we have is e to the negative 0.6 n is less than 0.001. And what I would do here is I would consider e to the negative 0.6 n equal to 0.001, and we'll deal with the inequality once we've solved that. And so if we take natural logs of both sides, log of e to the negative 0.6 n is the natural log of 0.001. And of course, the natural log and the exponential are inverse functions. So this becomes negative 0.6 n, and that's going to be log 0.001. And so n is going to be the log of 0.001 divided by negative 0.6. And so that gives us that n is approximately, let's say, approximately 11.5 when we calculate it. Now let's think about the inequality. Note it was a less than, but then we divided by a negative. So that would mean it was a greater than. So it's going to be n is greater than 11.5. N has to be an integer. So n is going to be equal to 12. The last part of the question says to write down an assumption that needs to be made for the model to be appropriate. And there's a few things here, such as rate of calls is a constant. So that's always a good one. It is just for 1 mark, so you really need just one reason. Other things would be the number of calls in non-overlapping time periods would be independent. And that may or may not be a good assumption, but it's an assumption that needs to be made for this model to work.